Hi, welcome back. We left off on the last video talking about the periodic table trends and how we can learn so much from the positions of the elements in the table. It turns out that columns are families, and these elements are very similar in their behaviors. For instance, column 1 are highly reactive metals, and we defined metals as elements that give away their electrons. That's because they have very low electronegativity, which was one of the other trends that we talked about in the last video. Electronegativity is the atom's ability to attract electrons to itself. And these elements over in column 1 have very low effective nuclear charge, which means the net pull of the nucleus on the electrons is weak. Well, you should expect to learn all of these various terms, the regions, the trends, and put them out on a blank periodic table as far as your quiz for this unit. And I will literally give you a blank periodic table and you'll just write all of these in. So make sure that you learn your families. For instance, if I say where are the halogens, that you would go and mark them off here in column 7. So that kind of ability with the periodic table is essential for success this year. Let's talk about something you should have covered in physical science, which is counting up protons, neutrons, and electrons in an atom. Let's say I gave you zinc, and on the periodic table you'd see it has a mass of 65 and a proton count of 30. So that's the general format. Now some periodic tables flip mass and atomic number, but this is the way I want us to adopt it. The lower left number is always referring to proton count, and the sum total mass is up here in the top left. So if I'm asking you to count the number of protons, neutrons, and electrons in this atom, you could do so in what way? Well, proton count is laid out here for you very nicely as 30. Okay? Neutron count is hidden up here because this is equal to the number of protons plus the number of neutrons. That's the mass of the atom. We say the electrons are so light they really don't factor in to the overall mass. These guys are given 1 each, atomic mass unit of 1, so we sum them up. So if the total mass is 65, then there must be 35 neutrons, which is 65 minus 30. And then electrons will equal protons if it's a neutral atom, and this is. If I vary the number of electrons, that's when we get charges, which we'll talk about on the next slide. All right, one more example. Let's say I'm giving you lead, and I'm giving you the particular lead atom that has 207 mass. On the periodic table you'd see its symbol number 82. So let's do this. How many protons? You tell me. I hope you said 82. How many neutrons? I hope you took 207 and subtracted 82 to get 125. And how many electrons? 82. I'd now like to talk about ions. What is an ion? An ion is when an atom has gained or lost electrons and adopted a charge. Here we see a lithium atom losing its electron and becoming lithium plus. We have to have charge balance. We can't have things disappearing. So this plus, this minus becomes neutral, and so it's neutral on the right, neutral on the left. We have charge balance. Well, to figure out the ion charge, we'd count the number of protons and we'd subtract the number of electrons, and that would establish the overall charge. So going back to the same example we worked on the previous slide, let's go back to zinc. And if I have a mass of 65, as I did on the previous slide, we went through and we said, okay, there are 30 protons, there are 35 neutrons, and we would put, for a neutral atom, 30 electrons, but let's change this. This is what an ion is. Suppose I only have 29 electrons, then this would be zinc plus. Or if I only have 28 electrons, then this is zinc 2 plus, which is the way zinc hangs out most of the time because it makes zinc stable to lose 2 outer electrons. And we'll talk about that more in a future chapter. But an ion is an atom that has lost an electron or gained an electron to adopt a charge. If we gain electrons, we end up with excess negatives, and we end up with a minus charge up here. We write charges in the top right corner above the symbol. Ion charges are somewhat predictable. We see that we can rely on this column 1 to be plus 1 and column 2 to be plus 2, and column 7 is often minus 1, and column 6 is often minus 2. If you think about it, this is what it takes for these atoms to get the octet. These guys here have 1 extra in their outer shell, which when they lose it, they go backwards to become noble gas-like from the previous row. Think about that, okay? If beryllium, which has 2 electrons in the outermost shell, would lose those 2, it would become like helium sitting up here, which is very stable. On the flip side, if we have a fluorine here, which is 7 outer shell electrons, it can get the octet by picking up 1 extra. Then it becomes like neon, very stable. So the extremely electronegative atoms up here in the top right, since they're so good at attracting electrons, they become negative as a way of reaching the octet. In contrast, the metals over on the left have such low electronegativities. They are not good at attracting electrons. In fact, they can hardly hold on to the electrons that they have. Therefore, they become octets by reverse. They go backwards a row and lose a whole outer shell. So it's reasonable that these positive cations, the cations, are smaller because they lost something, and these anions are bigger. What about all these elements in the middle? Well, it really depends on what atom they're interacting with, whether they are the winner or the loser of the electrons. They're mid-range on their electronegativities, so it is a function of their environment. What is an isotope? This sounds so much like ion, but it's a different thing. All elements have various isotopes, and that's when the number of neutrons is varying from atom to atom. All atoms of a given element have the same number of protons. They do not necessarily have the same number of neutrons. Atoms with the same number of protons but different numbers of neutrons are called isotopes. All elements have their own unique percent natural abundance of isotopes, and it's this variation that leads to atomic masses that are fractional, and I'll explain that. All right, let's consider neon. Neon has 3 different isotopes, neon 20, neon 21, and neon 22. Neon 21 is rare. Only 0.27% of the neon in the universe is of this type. Neon 22 is about 9%, and neon 20 is the most common isotope of neon. It has 90% abundance. Well, if we were to take what's the mass of an average neon, it would look a whole lot more like neon 20 than neon 21, because neon 21 is so unusual. So what we do is we get a weighted average, and you've done this in math class. We take the percent, and we have to write this as 0.0027 and 0.0925 and 0.9048. We write these percents as their fraction times the mass of 21 plus that percent times 22 plus that percent times 20. I have an example problem on the next page. Here's chlorine. The atomic mass of chlorine is derived from the fact that 75.77% of the chlorine in the universe is mass 35, or to be more particular, 34.97 AMUs, and 24.23% of the chlorine in the world is 37, or specifically 36.97 AMU. So this weighted average is the atomic mass is 0.7577 times that mass plus 0.2423 times that mass. That's the weighted average, 35.45. You see, 35.45 is a whole lot more like the 35 than the 37 because there's 3 times more of the 35. Gallium has 2 naturally occurring isotopes, gallium-69, which has this more precise value, which has a natural abundance of 60.11%, and gallium-71, which has that more particular mass and that abundance. What's the atomic mass of gallium? Alright, so what you should have gotten is that the atomic mass, the average atomic mass, is the weighted average of 0.6011 times 68.9256 plus 0.3989 times the isotope that's 70.9247. And when we punch this into our calculator, you should get 69.723, but we wouldn't write the 3. We're limited to 4 sig figs due to the percent. That wraps up Chapter 4, and hopefully you've gotten a much better sense for the atom structure and also the value of the periodic table.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.